Hello and welcome to a session on step-by-step calculations for analyzing a simple but realistic steam power plant. So the purpose of this is to give you some experience and show you how to go through step-by-step how to analyze a basic steam power plant, because there are so many applications both in the power industry as well as manufacturing and industry in general for all these pieces of equipment. So let's go ahead and get started. I want to set my stopwatch so that I can monitor the time it's taking to present this, because I want to try to hit just the right pace. I don't want to put you to sleep, but I also want to explain step by step how you make these calculations. So let's look at the problem statement first. I'm going to read this problem statement to you while you hopefully will read along. Steam enters the turbine of a vapor power plant. That's going to be H2O, steam vapor, at 600 psi, pounds per square inch absolute, and 1000 F. That's pretty hot. And it exits as a two-phase liquid vapor mixture at a temperature of 80 degrees F. Condensate exits the condenser at a temperature of 75 degrees F. Now that's going to be a compressed liquid at the condenser pressure, and is pumped back to the steam generator at 600 psi. The turbine and pump isentropic efficiencies are 90% and 80% respectively. The net power developed is 1 megawatt. Now, here's what we're supposed to find. Determine the steam quality at the turbine exit. That's one thing. The steam mass flow rate, 2, and the thermal efficiency of the power plant. Those are all very realistic questions to ask an engineer to find. Okay, so some immediate observations after simply reading the problem. We've got steam and water in our power plant. That's a phase change substance. We will be using steam tables. Each component described in the problem statement is going to be considered an open system, of course, running steady state, steady flow. Putting all 4 of the components together is going to comprise a system operating in a cycle. And hopefully that's going to be kind of familiar to you. The turbine and the feed water pump will be considered adiabatic. In other words, no heat transfer associated with the turbine process or the feed water pump process. You say, I didn't see that anywhere in the problem statement. Well, that's because we engineers, we read the problem statement, we have some familiarity with the equipment, and that's going to be our engineering model for the situation. Finally, the net power. Again, we realize we're producing power from a steam turbine. We need power to run our feed water pump, and so the net power produced, 1 megawatt, is going to be the turbine output power minus the pump power required. So those are just right off the bat common sense 101 things that we have in our minds. All right. I think this is such a complex problem, it probably makes sense to write down what's given. What's the given information in the problem statement, and what do we need to find? Okay, givens. Turbine throttle conditions, that's the inlet to the turbine, 600 psi and 1000 F. That's going to be superheated vapor. Turbine inlet condition is given. It's given as a two-phase liquid vapor mixture. That means find X, okay? And it gives you the temperature of the two-phase mixture. That's going to be a key thing to know. It also tells you that the condenser exit temperature is 75 degrees F. Now, a little thinking and sketching is going to show us that that state leaving the condenser for this problem is going to be a compressed liquid at the condenser pressure. Turbine efficiency and pump efficiencies are both given. What does that tell us? That tells us that neither the turbine nor the pump are isentropic. It says there's some irreversibilities going on in both of those, even though they are both adiabatic. So those are going to be modeled as adiabatic and irreversible. And finally, given the net power developed, W dot net, is 1 megawatt. Here's what we're supposed to find. The steam quality X at the turbine exit, the mass flow rate of steam, m dot, and the thermal efficiency, eta thermal. All right, well, let's get going. So far, we've spent 4 minutes just talking about the problem. All of us good self-respecting engineers need to start with a sketch, especially with a problem as involved as this one, because look, here's my sketch. Now, this sketch would border on a work of art. I've taken the time in PowerPoint to put together the little graphical elements to really make this a really nice professional looking sketch. Yours does not have to be this professional looking. Hand drawn, that can work. Doesn't have to be a work of art. Don't have to use a straight edge, just sketch. But let's look at what you do have to have, okay? Let's start at the turbine inlet, the turbine throttle, state 1. I've labeled state 1 and labeled the given information, okay? These are pipe. These arrows are basically going to be pipes, okay? Inlet to the turbine. I've shown this little trapezoid as a turbine. The steam is expanding. That's why I've shown it as this trapezoid. The steam is expanding as it's producing power. Look at this. I've shown a block arrow, okay, showing W dot of the turbine, W dot of the turbine. That's the turbine's output power. I've labeled the turbine efficiency, 90%. Labeling state 2, the exit of the turbine, and given information T2 is 80 degrees F. More on that later. Okay, here we've got a pipe that's going from the turbine exit into the inlet of the condenser. That's just basically a big vessel in which heat is transferred, let's say to river water. Heat is transferred. A condenser is a heat exchanger, but the steam leaving the turbine is condensed back into liquid. And so by gravity, the liquid's going to fall down into the hot well of the condenser. Okay, so little squares, the hot well of the condenser where the liquid is collected. Okay, and so I'm showing a block arrow, heat rejected from the condenser to our heat sink of the lowest temperature observed, 75 degrees F. That's going to be like river water. I've labeled state 3 coming out of the condenser. A pipe is going to convey that water, that compressed liquid water, into the inlet of a pump. I've shown, this is a schematic of a centrifugal pump going into the eye of the pump at state 3. That centrifugal pump spinning around, increasing the pressure of the feed water up to state 4. Okay, I'm showing W dot of the pump is less than 0. Power is required to drive the pump. Block arrow with W dot. And I'm showing that the pump efficiency is 80%. Here's my state 4, the exit temperature and pressure of the pump. And it's piped back to the steam generator, also known as the boiler. Okay, well, we have to add heat. So this is just feed water. It's just high pressure water, 600 PSI water. We've got to make steam. And so we are showing, okay, we're adding heat at a rate of some unknown value at this point. We need to find out what it is from a high temperature heat source at 1000 degrees F, the highest temperature observed, okay, 1460 R. So that completes my sketch, okay? We've just spent 4 minutes talking about the sketch, but do you see that there's no, if we didn't draw a sketch and didn't label our states, do you see that an engineering solution really would be useless to anybody else other than the author? And in fact, if you went back, if you were the author of the work and you went back 3 weeks later to look at your work without a sketch, you wouldn't remember what H1 was or H2 was. Got to have the sketch. Another thing you must have, and that's a TS diagram, a TS diagram. So you need to know that this needs to be second nature to you. And let's look at this. So now let's dissect this sketch that you must have in your solution. Okay, temperature on the y-axis, specific entropy on the x, the tried and true vapor dome. Now, on mine, I've drawn this to scale. This vapor dome on the TS diagram is to scale. And notice how it's not exactly symmetric, but it's a little bit symmetric, isn't it? Okay, so hand drawn is just going to be fine. Okay, This is nearly a work of art. Yours can be hand drawn. All right, well, let's start at the turbine. Okay, we're starting out into the turbine at superheated vapor condition, 600 pounds, 1,000 degrees F. Now, wow, we've got two process lines that describe the turbine. The first solid line is 1 to 2I. Your book calls this 1 to 2S. I called it 2I for the isentropic turbine. We don't have an isentropic turbine, but we're going to have to analyze that turbine in order to determine the actual process 1 to 2A. Now, your book calls this 2. I call that 2A, 2 actual. This is going to be the actual outlet state of our turbine. And I show it as a dashed line because that means it's adiabatic but irreversible. Solid line, adiabatic and reversible. Dashed line, adiabatic and irreversible. I've made that note on my sketch for you to go back and study as you need it. Okay, so here is our turbine outlet condition. We're going into the condenser. We go into the condenser and we reject heat. At constant pressure, a condenser process for steady state, steady flow is a constant pressure process. So here we go from 2A, all at constant pressure, and we hit saturated vapor. And for this problem, it says, not only are you going saturated vapor, you're continuing to cool the liquid in the condenser down to a subcooled or compressed liquid state, state 3, which is 75 degrees F. So notice here on my y-axis, I've labeled T2 is 80 given, and T3 is 75, 5 degrees cooler. Okay, we're making it around our cycle. Okay, now the pumping process. The pump increases the pressure of the liquid, increases the pressure to go back to the boiler. What I'm doing here on my sketch is I'm showing a dashed line, adiabatic pumping process, but I'm showing the entropy increasing from 3 to 4. We're also going to study the reversible pump, but I didn't show that for a very subtle reason. I didn't show that on my TS diagram. So irreversible, but adiabatic pump, process 3 to 4. And then finally, we hook into a pipe, a feed water pipe, and it's piped to the boiler. Here's our boiler inlet. Okay. And then we generate steam. We go clearly. This is a compressed liquid going into the boiler. It's not saturated liquid. It's not even to the boiling point yet at 600 psi. Okay. So we're heating the water, heating the water, heating the water. It gets to the boiling point at 600 pounds. We continue to add heat in that steam generator until it finally becomes saturated vapor. And then we continue to heat it until the flow becomes superheated vapor to go into the turbine. So that completes our cycle. Okay, so notice here, clockwise cycle on our TS diagram. We've now spent 12 minutes discussing this. Okay, so I think 4 minutes to simply read the problem and think about it. 4 minutes to create and discuss the equipment diagram. 4 minutes, and now going on 5 minutes to create and discuss the TS diagram. For you, this will be a time-consuming process. It will pay off for you if you hang in there and go through the process. Let's look at a big picture reminder and remind ourselves about the thermal efficiency of a system operating in a cycle. So I'm not getting off track. I'm just trying to give you the big picture. Okay. See this black box with a clockwise circle in it. All the equipment that you saw in that sketch, all the equipment that was depicted on the TS diagram, it's all fitting into this black box, it's jammed into this black box. Now, we're showing heat being added in the boiler, Q.H. And the heat source, the high temperature reservoir, is at 1460 R, 1,000 plus 460. We're making net power. That's going to be the turbine output minus the power required to drive the pump. We're rejecting heat from this black box. We're doing that in the condenser, and we're rejecting heat down to a heat sink of 75 plus 460 or 535 R. Now, it is my hope that you say, we can now calculate the maximum possible thermal efficiency, and that can give us something to check our work against, right? So if this black box were a Carnot cycle, and it is not, but if it were a Carnot cycle, we could calculate the Carnot efficiency by TH minus TL over TH. We've got that in our heads, okay? We don't need to go back and derive it. We could, but we're not going to. And we jam in the numbers to see that the maximum possible thermal efficiency for our power plant is 64%. That's the maximum possible thermal efficiency. So conclusion is, whatever number we get for our result had better be less than 64%. Otherwise, we've made a mistake. Process would be impossible. Okay, we're up to 15 minutes. And now I'm going to quickly review. This is a busy slide with a lot of words, so I'm going to quickly say, here's what we're going to do. Here's what we're going to do. Net power is given in megawatts. We're in the English system, and so we're going to need to immediately transform W dot into BTUs per hour for consistent units. We're going to be looking for M dot in pounds per hour. And so therefore, we're going to be looking at little W net. We're going to be seeking little W net in our calculations with units BTUs per pound mass. So that's a little bit of a units intro. Okay, here's going to be our solution steps. We're going to start at the turbine. We're going to start at the steam turbine, and we're going to analyze the isentropic turbine first. We realize we don't have an isentropic turbine. We've got an insulated turbine, adiabatic, but irreversible. We're going to apply turbine efficiency to get the actual work done by our turbine in BTUs per pound. Okay. Then we're going to determine the actual turbine outlet enthalpy using the first law in order to determine the quality at the Exeter turbine. That's what the homework problem is asking us to do. Okay. Then we're partway there. Then we will study the pump. Okay. We're going to look at the pump as if it were a reversible pump. And then we're going to apply pump efficiency. Okay, so here we go. Isentropic work. I got ahead of myself. Okay. We're going to study the pump as if it were reversible. And I'm going to remind you how we do that. There's some very neat skills associated with pumping an incompressible fluid. We're going to use that identity. Okay. We're going to apply pump efficiency then to determine the actual work required to drive the pump in BTUs per pound. Okay. Now that's going to give us the ability to calculate the net work, little w, in BTUs per pound mass. Now we know the net power. We know the net power that's given. And so that's going to enable us to determine M dot, the steam mass flow rate. W dot equals M dot times little w. Okay. So we're moving. That's going to be another thing we must do for the homework problem. Then we're going to study the steam generator heat added. We've got to have that for the thermal efficiency. So that'll be one of our final steps. And so then finally, we need to find what's the thermal efficiency of the power plant. It's the energy solder of the energy that costs. What we're seeking to do, if we own the power plant, we're seeking net power, and what it costs us is the fuel required to run the steam generator, Q dot H. Okay, we're up to 18 minutes. So we haven't put pencil to paper. We haven't looked at any properties yet in the steam table. We haven't done anything with our calculator. But we've done a lot of good pre-work so we can sail through the rest. Okay, first step. Transform the net power units. Okay, and so we've got 1 megawatt, and so we're going to apply our conversion factors, 1,000 kilowatts per megawatt. In the back of the book, look up, there's 3,413 BTUs per hour in 1 kilowatt. Okay, and so it looks like our net power is 3.41 million BTUs per hour to make 1 megawatt. So that's our first step, getting net power in BTUs per hour. So looking ahead, we're going to need that. Okay, next step, we're going to analyze the turbine. Here's a schematic of the turbine alone. The first thing we're going to do is look at the isentropic process, but the very first thing we need to do is determine H1. What's the inlet enthalpy? Because we're going to be using the first law. Okay. Also, we're going to look up S1. We're going to look up the entropy at state 1 to study the isentropic turbine. Okay, so here we go. We're going to go to the back of the book, 600 psi, 1,000 degrees F. So we're going to write down H1 is 1517.8 BTUs per pound, and S1 is 1.7155. We write that down in our solution and then move on. So looking ahead, we're going to study the isentropic turbine first. Okay. Let's analyze the turbine isentropic process 1 to 2I. And I've circled it here on my TS diagram sketch. A little clip from the TS diagram. This is what we're looking at, this vertical line, isentropic, constant entropy process. And what are we trying to do? What we're trying to do is find, so let's look ahead in the solution. We're trying to find W sub I, little w sub I, BTUs per pound that the isentropic turbine would produce for each pound of steam going through it. Okay, so let's see. So we're going to need to determine, so we know what S2I is, don't we? S2I equals S1. So here's S1, and then here's S2I. I should say in my solution, instead of equals S2, that should say S2I. S1 equals S2I, 1.7155. All right. Now, how am I going to determine the outlet quality? Well, I'm underneath the dome, so I need to look up S sub G and S sub F. That's off my little sketch here, the entropy of saturated liquid. So I've looked these two up in my temperature table at the given temperature of the condenser, 80 degrees F. So this temperature here is 80. That's how I knew to go to the temperature table. All right. So I've written down S sub G and S sub F. Here they are. And looking ahead, I've also written down H sub G and H sub F because I know I'm going to need those. So I've written down 4 numbers out of my temperature table at the temperature, operating temperature of this saturated mixture, 80 degrees F. Okay, everybody see how to get that? All right. So I solved for, okay, great. So I've got those. What am I looking to do? I'm trying to find X2 isentropic, X2I. I remember the definition. It's a ratio, isn't it? X2I is the quantity S2 minus SF2 in the numerator divided by the total distance, SG2 minus SF2. And so I get 83.5% quality at for the isentropic situation. That's not the answer to our homework problem. That's going to enable us to get there. So we're going to solve for H2 isentropic. Okay. And we use the definition of quality again. H2 isentropic is X2I that we just found times HG2 tabulated, okay, plus whatever's left over, 1 minus X2I times HF2. This is why your mastery of chapter 3 is so important. We're solving for H2 isentropic in order to find the isentropic work. The first law, we apply the first law for the isentropic turbine, and here it is. You say, well, where's Q? Where's Q isentropic? That's 0. It's adiabatic. So this is I didn't drag you through all the steps. Work isentropic is H1 minus H2I. Okay. I'm going to trust that you can go back and derive this from the basic statement of the first law, open system, steady state, steady flow. Don't just use this as a formula, as a given formula. It's not. It's a statement of the first law. So we just found W isentropic 594.17 BTUs per pound. Say, okay, now I'm a little lost. Well, we're trying to determine the actual work produced by the turbine. This is going to get us there. We determine the isentropic work, but we're given the turbine efficiency. So we remember to ourselves, what's the definition of turbine efficiency? Definition of turbine efficiency. Well, you can go to your book, okay, and look up the formula or use a little common sense. So I'm circling the common sense. The turbine efficiency, what would you expect the actual power from a turbine to be compared to the isentropic power? I would expect it to be less. I'd expect, and the efficiency is always a number less than 1. So instead of seeking out the formula, I'm going to suggest that you could write down the statement of turbine efficiency on your own, and then also say, wait a minute, okay, I've got an isentropic work of 594. My actual turbine work, WA, associated with Prof dash line 1 to 2A, it's going to be less than that. In fact, it's going to be 90% of that. So there it is. Boom. 534.75. Okay. Now, in our homework problem, it says, what is the actual quality at the outlet of the turbine? And all we did was just find the actual turbine work. Well, we need the actual outlet enthalpy, actual outlet enthalpy of the turbine outlet. Well, we can use the first law to solve for that. The first law for the actual turbine is, okay, well, let's see, Q at 0 minus W actual equals H2A minus H1. Got that in our head. We do the algebra in our head to write down the first law for the adiabatic irreversible turbine. Here it is. W actual is H1 minus H2 actual. So we can solve for H2 actual, 983.05 BTUs per pound. Whew. Okay. Well, now we can go back. We can go back and say, well, now that we have H2 actual, we can use the definition of quality to back calculate the steam quality at the turbine exit. And this is what's asked for in the homework problem. And so we'll back calculate. Now we have HG2 and HF2 from before. We already wrote that down. We have H2 actual. So we can use our definition of quality to determine that X2A is 89%. 89% is the steam quality at the turbine exit. Okay. We've been through a lot of work already, and we've only covered 25% of the equipment. We've been working at this for 27 minutes now. Okay. Hang in there. Okay. All right. But we've got part of the homework licked. Now we're going to move to the feed water pump. Okay. Our job is to determine what is the actual work needed by the feed water pump. Well, we've got to go and we've got to study if the pump were reversible first, and then we will apply the pump efficiency to determine the actual pump needed. So now we're going to go back and we're going to review your textbook from chapter 6, the reversible work for a pump, W dot over M dot, W reversible for a pump. So this is a review of chapter 6, and I've tried to show a sketch. Here's our pump. Okay. Ignore state 1 and state 2. This is just sort of a sketch of my pump. Some reading from your chapter 6. Okay. And it turns out that the reversible work for the pump is given by minus the integral of VDP for an open system, steady state, steady flow, no changes in kinetic or potential energy. So now I'm circling the reversible work for a pump in the absence of changes in kinetic energy. We don't have any of those, is minus the integral of VDP. I'll remind you that for a pump, water is basically an incompressible fluid. We take V out of the integral. We get this relationship. The reversible work, W dot over M dot for the pump, is equal to V, the ingoing specific volume, times the pressure difference, P1 minus P2. And so over here, I've made it in a bigger font. W reversible of the pump is equal to V at the inlet times P at the inlet minus P at the outlet. That's going to be reversible work for the pump, and it's going to be a negative number. P inlet is a low pressure, P outlet is a high pressure, low minus high. W reversible pump is going to be a negative number. All right, well, let's go get some numbers. Look at the reversible work inputs. We need V3. So here's a little screenshot of my TS diagram. Okay, so we need V3, inlet of the pump. Okay, and let's see, we also need P3. Okay, so here's the work needed for that. Okay, so let's see, the temperature at state 3 is 75 degrees. So I'm going to go to the temperature table in the back of the book. I've got to interpolate between 74 and 76 degrees F to get that V3 is 0.01606 cubic feet per pound. Okay. I need the pressure at the inlet of the pump. Now, I know the condenser pressure, the condensing liquid, vapor to liquid, occurs at 80 degrees F. So I've got to go to my temperature table at 80 degrees F and see what the saturation pressure is at that temperature. And the saturation pressure is 0.5073 pounds per square inch. And so here's my condenser process. It goes over constant pressure and temperature until it becomes saturated liquid, and then cooling, it continues in the condenser to subcool the liquid. And so this is a constant pressure process 2A to 3. Okay, whew, that's a lot, but I was able to write down P3 is 0.5073 pounds per square inch absolute. That is a low absolute pressure compared to 1 atmosphere. Okay, and also I wrote down, well, what's P4? What's P4? I'm going to need that for my reversible work. P4 is 600 pounds per square inch absolute. Now we've got some engineering calculations to do. We've got our properties. Now we got to do our engineering calculations. All right. So back to the calculator. The reversible work of the pump is minus integral VdP, or V3 times P3 minus P4. Here's those blue cells. I laboriously went through and showed you how to get them, okay, out of the steam tables, okay. So I'm going to plug and chug, okay, and one thing I didn't mention, here's my P3. I have converted that to pounds per square foot, 73 pounds force per square foot. P4, 86,400 pounds per square foot to get my units right, okay. Be very aware of that. So look at those units that I've put in my solution, okay. And so the reversible work of the pump is calculator work, negative 1386 foot-pounds force per pound mass. I've got to apply my conversion factor that I know, 778. Foot-pounds force equals 1 BTU. And so finally, the reversible work of the pump is negative 1.78 BTUs per pound. This is a lot, isn't it? We've been going at it for 33 minutes now, okay? And we're not finished with the problem, okay? Reversible work of the pump. W dot over M dot, negative 1.78 BTUs per pound. Now, what's the actual pump work? Well, let's see. You can either go to the text for a formula, or you can kind of figure it out on your own. What would you expect the power required to drive a real-world pump be compared to a reversible and adiabatic pump? What would your common sense tell you? More or less power required if the pump were irreversible? My intuition says it would take more power to drive that pump. And so the pump efficiency is given by pump efficiency, W reversible over W actual, the smallest number divided by a bigger number. And so there's the reversible work of the pump we calculated, pump efficiency 80%. So we're just going to scale it up. 1.78 divided by 0.8 is negative 2.23 BTUs per pound, the actual pump work required, W dot over M dot. Woo! We're getting there. Trust me, we're getting there. 34.5 minutes. Okay. Let's see, what have we done? Now we got to recap. We analyzed the turbine and got W turbine actual. We analyzed the feed water pump. We got W pump actual. And we just wrote them down here. Here they are. All I have to do to get the net work, BTUs per pound, W dot over M dot, is to add those two together. So the net work is 532.5 BTUs per pound. Now we can determine the mass flow rate because W dot net was given. Here it is. All the way back when we started it, 8 minutes into this. It was, it looks like 3.4 million BTUs per hour divided by W net. Okay. That gives us the mass flow, 6,411 pounds per hour to produce 1 megawatt of power. 6,411 pounds per hour. So now we've really got a leg up on our homework problem, but we've done a lot of work to get there. Steam mass flow required. I've spelled required wrong. 6,411 pounds per hour. Now we're going to move to analyzing the boiler. Why are we doing that? Because we need the boiler heat input to determine the thermal efficiency, and then we'll be home free. Okay. Well, let's see. Let's look ahead to the boiler. Let's see, what's the inlet state of the boiler? It's state 4. And we didn't calculate H4 yet. So we're going to need to calculate H4, right? We need to write the first law for the actual pump. Okay. And we can do that in our heads. I don't have it on this slide. The actual pump, adiabatic pump. So Qn, 0, minus W of the pump, we know it, equals H4, pump outlet, minus H3. Okay, so we need H3 for the pump. We didn't determine that. We need H3 for the pump in order to get H4. So we're going to backtrack. We're going to backtrack a little bit and go back to our temperature table. Going into the pump, the temperature was 75 degrees F. Okay. And so H3 of the pump, we're going to interpolate to get H3 of the pump is 43.09 BTUs per pound. That's the pump inlet enthalpy. We determined that W actual of the pump was negative 2.23. We did that in previous work. Okay. So now we're going to apply the first law for the adiabatic pump in order to get H4. So H3, 43.09, W of the pump actual. So H4, the enthalpy leaving the pump is simply going to be the inlet enthalpy minus the work of the pump, which is going to boost up the enthalpy to 45.32. So there's H4, that's going to be the inlet enthalpy to the boiler. Okay, we've got to do that. There is no other way to get the enthalpy going into the boiler other than doing that analysis of the pump first. Okay. Now on to the boiler. We're going to write down the first law for the constant pressure boiler process. Well, Qn minus W out, the boiler is not lifting a weight. There's no shaft coming out of the boiler. W out is 0 for the boiler. Okay. Equals, so Qn minus W out for the boiler equals H out, H1 minus Hn, H4. QH is H1 minus H4. Okay. Woo, great. We're getting somewhere now because we already determined H1 from previous work. H4 we just determined by analyzing the pump. So calculator work is easy. QH is simply 1472.5. H1 minus H4. That's the analysis of the boiler. We've been going at this for 40 minutes now. Now, we've done an awful lot of analysis. It's my hope that this is going to pay off for you in the long run. Now we're up to the thermal efficiency of the power plant. We remember in our minds that this important, I've circled it. The thermal efficiency is the energy sought over the energy that costs. If you're the owner or the manager of this power plant, what are you seeking to do? Well, you're seeking to make net power or net work. Okay. And what's costing you to run? What is costing you to stay in business? It costs you to run that boiler. You have to pay for the fuel to run that boiler, no matter what the heat source is. Okay. That's QH. Okay. So W net over QH. Wow, we've got all those. Calculator work is easy. W net is 532.5. QH we just found 1472. And so the thermal efficiency of this power plant is 36.17. That's the thermal efficiency of the power plant. The energy sought over the energy that cost. That's a big conclusion. If you can get through all these processes, this is going to be a huge saleable skill for you when you're out seeking employment as an engineer. This can be big for you. So hang in there and practice. Now that's the end of the homework problem, but I want to complete the analysis of the power plant for the purpose of this video. So we've been working 41 minutes now to get all the homework questions answered. Let's do a little bit more. Let's analyze the condenser process. Remember, that's state 2A coming from the turbine, 2 actual. Okay. State 3 is going into the pump. Okay. 2A to 3. The condenser is operating at constant pressure, and its purpose is to condense steam back to liquid so you can pump it. Okay. And so there's no output power from the condenser. It's just a heat exchanger. Okay. So W for the condenser is 0. Okay. Here's the visualization on our TS diagram. We're condensing. Look at that. We're not quite saturated vapor, but we're a pretty high quality vapor. We've got to get all of that condensed, not only back to a saturated liquid, but for this problem, a subcooled liquid. Okay. So at constant pressure. And so we'll write the first law, H2. So let's see, Qn is going to be H3 minus H2A. There it is. QL, that's the heat rejected, H3 minus H2A, the heat, but it's going to be a negative number. Q added is negative. It's going to be rejected. And so sure enough, this is all from previous work. H2 actual, 983 BTUs per pound. H3, 43.1 from previous work. BTU, subtract those two. QL is negative 940 or 940 BTUs per pound, Q dot over M dot, negative 940 BTUs per pound. Now, this enables us to verify the first law. It enables us to numerically check our work. Now, I have to tell you that not only as a student, but even as a practicing engineer, I make mistakes from time to time. Sure, I make mistakes just like everybody makes mistakes. And so I use the first law for a cycle to check my work, and you can too, all right? And so now we've done all of the work. We have calculated QH, that's the boiler heat input. We just calculated QL, the heat rejected. We just calculated W net, BTUs per pound. Does QH, we look at our sketch, these things had better balance or we've done something wrong. And so to check our work, sure enough, in Excel, my numerical work checks. Does QH minus QL equal W net? It sure does. Okay. All of those in BTUs per pound. So so you can use the first law for a cycle to check your work when you're analyzing cycles. Let's recap. So we are getting close to the end. You say, thank goodness, I didn't think this guy was ever going to stop. We've been going 44 minutes now. Let's recap because we've covered a lot of material. We started with a sketch. In fact, we started with two sketches. We drew with an equipment diagram that pinned down, that described the states and the given information. We also drew a TS diagram, and here it is, okay? We observed on the TS diagram that we're going in a clockwise manner. Wow, and we drew this sort of offline. We drew this schematic diagram, and we see the similarity between the TS diagram clockwise motion and the clockwise block arrow within this black box, okay? We analyzed the steam turbine first, and we looked at work, BTUs per pound, W dot over M dot. Okay. Then we moved to the pump, and we analyzed the pump work needed, BTUs per pound. Then we determined the net plant output. We simply added those two together to get the net work. One was positive, one was negative. Okay. We studied the steam generator or boiler to get QH. That gives us all we need. W net and QH is all we need to determine the thermal efficiency. And we got it. And we checked off everything we needed to do the homework problem that way. Now, one thing that just came in my mind that's not on the slides is, do you see that this analysis would be basically impossible if all you did was seek out formulas in the book? Okay. Successfully getting through this complex problem requires you to understand the first law, the second law, and how to put things together. It's simply looking for a formula for thermal efficiency will never get you to the promised land for this complex of an engineering analysis. Now, you might say, are you interested in the step-by-step numerical solution? I'm willing to share my Excel file that I use to solve this problem. So all the screenshots of the numerical work are disclosed in Jay's Toolbox out on VT domains. Okay, and this is a screenshot of it. So rather than taking the time to go live, if you go to Jay's Toolbox on VT domains, there's the address. Okay, you can download this by clicking the download button. How you navigate to this, if you can't quickly write this down, is click on Jay's Toolbox, click on the Toolbox menu. Under the submenu XLS Docs, that's Excel Docs. And then finally, heading under that, Excel Thermal Systems, Excel Thermal Systems. That's where you can click on download the Excel file that's the full solution to this problem, complete with screenshots of the steam tables, as well as the numerical work required to get all this done. Okay, one last remark. This is a screenshot of the John Amos Power Station that's in West Virginia. It's west and north of Charleston, West Virginia. And so as you can see from the cooling towers, as you can see from the three power exhaust stacks, there's 3 units at the John Amos plant. Gosh, I'm pretty sure that I was going to say the Kanawha River. I'm not exactly sure which river that is, providing the cooling water. Each of those power generation units operates at over 1,000 megawatts each. So in this image, you're looking at 3,000 plus megawatts of electric power generation capacity right there in front of your eyes. This homework problem had a power plant making 1 megawatt. And so to get you somewhat comfortable with units, the homework problem would be a very small version of this power plant. However, there are many industrial sites, I'd say industrial sites, that might be looking at power generation of this magnitude, of maybe 1 megawatt or a few megawatts or something like that. So this homework problem was not unrealistic, and it is a wonderful chance for you to improve your skills, not only in analyzing an entire power plant, but also analyzing components piece by piece by piece. And so here, let's we'll stop sharing because we're near the end. What components do you have the opportunity to analyze by itself? You can now analyze a steam turbine by itself. You can analyze a pump by itself. You can analyze a steam generator by itself. And you can also analyze a condenser by itself. And so I want to encourage you to hang in there and practice this type of problem, whether it's this specific problem or something that's been assigned to you differently in class, but hang in there, try to master each of these elements of the steam power plant, because it's going to give you tremendous engineering skills as you move forward, both in doing tests, both in taking tests to get a good grade in your class, and then beyond in practicing your engineering skills and getting through the last 2 years of your mechanical engineering class, because you will revisit these components in the last 2 years of your classes as well. So good luck. Let me know what I can do to assist you in getting better and better at these type of analyses.